Parametric ReLU. Let us learn about Parametric ReLU activation function. In the previous lectures, we learned about different activation functions. The main question here is, why do you want to learn about this Parametric ReLU activation function? What is the specific need of Parametric ReLU activation function? Let us understand this first, because see, whenever you are learning something, you should know why it is required. Then only it makes sense to learn about what it is and how exactly it is functioning inside. So let us first see what is the requirement of this function. Why do you need this in the first place? Okay. When we were learning about different activation functions, in the early lectures, we had seen that when we learned about, let us say, sigmoid activation function or a tanh activation function, in all those, we had seen that these activation functions faced a problem called as vanishing gradient problem. Because of this vanishing gradient problem, the gradient used to vanish when it is going towards the early layers, which would mean in your neural network, the early layers of your neural network, they will stop learning. This was the problem. This is when we came up with ReLU activation function, and with ReLU activation function we were able to solve this problem of vanishing gradient. But when we solved vanishing gradient problem, ReLU introduced a new problem. This problem was called as dying ReLU problem. This we discussed in detail in the dying ReLU lecture. After that, we had to find some way using which dying ReLU problem can be rectified. This is where we came up with something new called as, that is a modification on this ReLU activation. It was called as leaky ReLU activation function. In the last lecture, we learned about leaky ReLU activation function, though we had seen how it is overcoming the problem of dying ReLU. But again, like how ReLU introduced a new problem, leaky ReLU also introduced a new problem, which is called as the problem of fixed parameter alpha. So it introduced a hyperparameter called alpha, which you had to fix before training. So because this was a fixed constant parameter, the problem you had is, we discussed that commonly you will use something like 0.01 for this alpha. But is that optimal? This is the question we had. So it turns out that in many cases, the optimal value need not be this, and you may have to hit and try different chances in order to understand, in order to tune it and understand which exactly is the optimal value of alpha. And it may even happen that in your neural network, let us say you have a large neural network, different layers may need different values of alpha, or it can be that different neurons may sometimes need different values of alpha, or different channels may need. So in all those cases, choosing a fixed alpha was always a problem. This always caused this problem during optimization. So obviously the next thing we think is, how can we get rid of this problem of having a fixed hyperparameter alpha? This is where Parametric ReLU comes into action. So this is the need of Parametric ReLU activation function. With Parametric ReLU activation function, you no more have this problem called as the problem with fixed parameter alpha. Okay, so let us first understand what is the core idea behind this and how it is different from your leaky ReLU activation function. Okay, so I'll erase this off. The core idea that is behind Parametric ReLU activation function is this. Instead of having a fixed parameter alpha, what you are going to do is, you will keep this alpha open for the network to learn. The same way your neural network will learn different weights, that is in each neuron, you want to learn weights, the coefficients, that is the main task of this neural network. The same way it is learning all those weights, we'll let this neural network only learn about this parameter alpha. So we are not going to fix anything. Instead, whenever you want this alpha value for your negative inputs, you will let your neural network learn this during training. So let us write the function first, then we'll be more clear about how alpha is affecting here. In case of ReLU, in case of your normal ReLU, what was the function that we had? the ReLU function f of x, this used to be like this: f of x is equal to x whenever, that is if x is greater than 0, and you had 0 whenever x is less than or equal to 0. This was the case in case of ReLU activation function. Thereafter, we came with leaky ReLU. Then what was the difference? The negative scenario, whenever x is negative, instead of keeping this as 0, we decided to keep it as alpha into x, right? Alpha into x. So this alpha hyperparameter is the new problem. Then we are now introducing parametric ReLU. How does the formula look in case of parametric ReLU? If it is parametric ReLU activation function, then this formula will look the same, the exactly same one as what you learned in case of leaky ReLU. So the next question is, if the formula is exactly same, then where is the difference? Okay, this is what we want to learn. Before that, this formula you may also see in other forms. That is, instead of this, you can also write it as, see, max of, this is also the same formula. Instead of writing it this manner, I can also write it as max of alpha x or x. Okay, this also means the same. I just want you not to be confused if you see this particular format somewhere else, or in some places you may even see it in a different format, something like this. You can also write it as max of 0x plus min of 0x into a, or I'll write a first, okay, so that it's visible. I means alpha into min of 0x. So this is another way. So whether you write it this way, or you write it this way, or you write it this way, this all means one and the same. It's just different ways of mathematically expressing it. Okay, so just keep this in mind. Okay, so what were we discussing? We were discussing about what is the difference parametric ReLU is bringing in over the normal leaky ReLU that we had. If this equation is exactly the same, I'm telling you these equations, these are exactly the same as that of leaky ReLU, then what is the difference parametric ReLU is bringing in? In order to understand this, you want to understand the gradients and then how these values are getting updated. Okay, first we'll take the gradient of the function, that is f of x is this. We'll take f dash of x, the gradient with respect to x. If you do that, you will get 1, that is derivative of x with respect to x will be 1. So 1 is the gradient whenever x is greater than 0. And what about alpha x? Derivative of alpha x with respect to x will be alpha. So alpha is my derivative if x is lesser than or equal to 0. This also looks the same as what we saw in case of leaky ReLU. So again you may think, okay, there is no difference till this point. Then what can be the difference between leaky ReLU and parametric ReLU? This is where you want to understand where this gradient is used and how updations are done during training. That is where the difference comes in. First thing we'll understand is, during your training, let us say you have a neural network. When you are training it, you will back propagate loss. When you are back propagating loss, you will try to update different weights of the neurons. So you want to update weights of the neurons, and in case of parametric ReLU, you want to update the value of alpha as well. So let us understand how the value of those weights get updated and how the value of this alpha gets updated. When you understand this clearly, you will understand the difference between leaky ReLU and parametric ReLU. Okay. So first we'll think about weights. If you want to update weights, there is some weight W. How do you update? You take gradient, that is this gradient. Gradient you are taking with respect to x, and using that gradient, what will you do? This gradient will flow backwards. That is, whenever x is positive, your gradient is 1. Whenever x is negative, your gradient is alpha. This gradient is going to flow backwards and update your weights. So this part is same as what we learned in all the previous lectures. In neural network, how the weights are getting updated, the same procedure follows. According to the derivative, you will update weights according to that extent. The difference that you want to learn here is how you are going to update value alpha. For this, you want the derivative of the function, that is, this is the derivative, but this is with respect to x. You want the derivative of this function with respect to alpha so that you can update values of alpha. So let us see how to take derivative with respect to alpha. Derivative with respect to alpha is del f by del alpha. So with respect to alpha, if you take derivative, if you see this, x is the term. If you take derivative of x with respect to alpha, what will you get? There is no alpha term involved here. So derivative of this x with respect to alpha will be 0. So whenever x is greater than 0, your derivative with respect to alpha is 0. What about this term alpha x? If you take derivative of alpha x with respect to alpha, you will get x. So it will be x whenever x is lesser than or equal to 0. So this is the most important part in updating alpha. If you want to update the value of alpha, you update according to this derivative. The derivative with respect to alpha. Do not update according to this derivative. This is used for updation of weights and this is used for updation of your parameter alpha. How will you update? Let us say your new value of alpha, updated value will be whatever is the old value, that minus you will have eta, which is learning rate, into the gradient. Let us say del f by del alpha, something like this. So according to the influence that is brought in by this derivative, you will be changing the value of alpha. This is how the value of alpha changes and this is how alpha is also getting learned. If you see the previous case, in case of leaky ReLU, alpha was a fixed constant. You were not changing this during training. Here, when you're training the model, not just the weights, alpha is also getting updated. So in each time, each pass, whenever you are updating the weights during backpropagation, you are going to update alpha as well. So this is the difference between leaky ReLU and parametric ReLU. Okay. So you can think of this something like this. There can be many scenarios. One can be that, let us say you are having a lot of layers and early layers which would face vanishing gradient problem if it is in the older activation functions. Maybe the requirement is that you will need a larger value of alpha in the early layers and in the later layers here you may need a smaller value of alpha because these are close to the loss. So in such cases, training will automatically adapt such that alpha values in the early layers will be updated to a larger value and alpha of the later layers will be updated with a smaller value. So these things automatically your training cycle will take care of. So you no more have to worry about how to set the value of alpha. Okay. Maybe you can think of it like this. Alpha will start from a very small value, something a very small value. And then during training, different layers or different channels, whatever it be, they will take values of alpha accordingly. You can think of it like this. Next question is, how or why does this parametric ReLU perform better than leaky ReLU? This you should understand. What is the reason because of which it will perform better? One thing you can think of is, there may be some scenarios where your negative values, they may carry some important information. In case of leaky ReLU, when you're fixing alpha to 0.01, many times that important information will be diminished so much so that information won't be evident at all. So in order to handle such scenarios, if you let alpha be trained on its own, whenever that is important, accordingly, your training cycle will train alpha and alpha will have a required kind of values there. So one more thing you want to see here is, this importance will also not be fixed. In each layer, maybe the importance is different. So in those cases also, your training will automatically take care of all these problems. Okay. Next thing is, where will you use this parametric ReLU? Where exactly are you going to use parametric ReLU? Here the answer is, you can use in case of, let us say, cnn's you use for image detections, also those things. There this parametric ReLU can be useful, especially when, let us say, you are having some image. If you are having some image and different channels, you want those channels to have different values of alpha. So in those cases, parametric ReLU can help you in training different alpha for each of those channels. This can be very helpful. Similarly, in GANs, you make use of parametric ReLU, or you can say any of the object detections models. Generally, parametric ReLU is a good option. Okay. Before we conclude this lecture, let us also understand what are the disadvantages, so that you will understand why do you need more activation functions, what scenarios are to be handled, and why should you need more activation functions. So what could be the disadvantages? Just think about this. What could be the disadvantages? One is, because you are training, there is a very obvious disadvantage that is going to come in, that is called as overfitting. What is overfitting? Overfitting means when you are having a lot of neurons in your neural network, your values of alpha may get trained so much in order to suit the input data, the training data that you used. What will be the effect? Because your alpha is so much over adapted to the training data, it will give perfect looking results in the training data. But as soon as you give test data which is different from this training data, that is, if you give any input from outside, then it won't give you the perfect result, because your model is now not robust. It is so much overfitted with the training data. So this is the problem with parametric ReLU activation function. One more thing you can say is, in some cases, your optimization may get a bit tricky. That is, let us say your alpha became too large. Then what can happen? Your function may become close to linear. So this is a problem we discussed in the previous lecture also. That is, when you should not fix alpha to a larger value. Let us say this is your graph. So in this graph, your ReLU will look something like this. On the positive, it will be y equal to x line. On the negative side, it will be 0. This is your normal ReLU. With leaky ReLU, we had seen that you will have something like, in the y equal to x, it will remain the same. But on the negative side, it will be something like this, a very small change from the 0. But what happens if you increase the value of alpha? This line, this will come closer to this side. Okay. And what happens if it comes here? Then the whole purpose of having an activation function is lost here. Why is it lost? Because think about this. Why do you want an activation function? What is the purpose of having an activation function in a neural network? The whole purpose is to introduce non-linearity in the neural network. But if your activation function becomes a linear line, then what is the whole purpose of having this? Non-linearity introduction is the whole purpose of your activation function. Then if your activation function becomes a linear line like this, then it will introduce no non-linearity. This is where, when you let alpha train itself, if the value of alpha increases, then your negative side may shift slightly towards here. And if it comes anyway close to linear, then the whole purpose of having this activation function is lost. So this is one thing you have to be careful about. Okay. And also it will be a bit sensitive to the initial value that you initialize with. So even if you are training, you should have some initial value from your training, from where training starts. So this training can be a bit sensitive towards the value you are initially setting. Okay. So these are the problems with the activation functions. So where do you use it? One main usage is in CNNs, especially when you want object detection or something. You may want different channels in your CNN have different alphas, and this can be done easily using training. Okay. Okay. One thing, what did I mean when I say channel? When I say channel, in each layer of CNN, you may want to detect different sort of things. That is, you may want to detect different characteristics. So each of those characteristics can be caught in different channels. One example is, let us say you want to do some sort of work on an image. Then you can have three channels. These three channels can correspond to red, green, blue. Why? Because you know that with these colors, you'll be able to make any color. So using red, green and blue, if you can make any color, then identifying the effect of red, effect of green and effect of blue separately will help you to identify the characteristics of this image. So in such cases, for each channel, you may want different values of alpha because the things that they have to identify are different. So it need not be three channels. I just gave an example. Let us say you have some image, something like this 56 by 56 image or something. On that, you may want, let us say, 128 different channels in order to understand 128 different features of the image. Then each feature can be identified by each channel. You may want 128 such channels or maybe 256 such channels. Whatever be the count of those channels, you can have those many different values of alpha if you do training using parametric ReLU. So this is where parametric ReLU activation function is important.